Welcome to the very last video of the unit. Woo! So let's start off. This is just, it's a lot of little different pieces of information. We're just kind of wrapping things up. So one piece of information you're going to want to know is that metal oxides are basic. So if you have a metal oxide plus water, it ends up creating metal hydroxides. So we're going to write the net ionic equation for when solid potassium oxide is dropped in water. So we'll write out the metal oxide, K2O, dropped into water. It's going to react to form metal hydroxide. So it would be, we'd have 2KOH. However, they're asking for the net ionic, so I'm going to rewrite this now. I have my solid and my water reacting to form. This is a strong substance, so I know it dissociates. And metal oxides aren't super soluble, so we're going to keep them whole on this side. Here we have, this guy is actually a solid, and that one is a liquid. All right, so next. Complex ions. Complex ions are charged species, so complex ions have a charge, and they are consisting of a metal ion surrounded by ligands. So many transition metals, including aluminum, which we don't consider a transition metal, will act as Lewis acids, where they will accept electron pairs. And then the ligands, which are surrounding the metal, will act as a Lewis base. In other words, they will donate electron pairs. Some examples, some common ligands would be water, ammonia, chloride, and cyanide. So here is an example of some complex ions. We have cobalt with water as its ligand. We have 6 of them. We have copper with ammonia as its ligand. And here we have silver with ammonia as its ligand. So metal, ligand. 6, 4, and 2 are the most common coordination numbers. So these right here are the coordination numbers. 6, 4, and 2. So here's an example of silver accepting lone pairs from ammonia. So notice how silver has a +1 charge. We're going to add ammonia, which has no charge. So it's still going to have that +1 charge at the end. Now there's a trick to knowing how many ligands will attach. So let's go ahead and look at that. That'll be the next slide. So it's good to know, though, that they form in a stepwise pattern. There are steps, step 1, step 2, and then here's the total. So you can see that the silver attaches to the ammonia, and there's a K for that, an equilibrium value. And then we're going to take this and whoop, it starts us off. It will attach itself to another ammonia. Now it has 2 ligands. So the coordination number here is 2. It's got a coordination number of 2. And if you want to figure out the equilibrium constant for the total equation, you're going to use the K1 times K2, and you'll end up with the total K value. Okay, so here are some tips. Wait, oh no, where's that slide? I thought I had one. Okay, not yet. We'll get there. So a copper to nitrate solution is mixed with concentrated ammonia. Write the net ionic equation. This is something that can show up in an FRQ. It has shown up in an FRQ. If you look up old AP tests, you'll find stuff like this. So we will do this one in a couple of slides, but I just want you to know that the terms excess, concentrated, or saturated will always be used to reference the concentration of the ligand in the solution. So here they're saying it's mixed with concentrated ammonia. So that means that ammonia is our ligand. This is a hint. We're dealing with ligands. In order to make a complex ion, there must be an excess of the ligand. So using the word excess, concentrated or saturated, means that we have a lot of it. So here's what I was promising, some tricks on determining the number of ligands. There is a general trick. What you do is you take the charge of the cation and multiply it times 2. So like here we have the charge of 1 times 2 is equal to 2 ligands. However, sometimes it doesn't work, unfortunately. Like here with aluminum with a +3 charge, if you multiply that times 2, you end up with 6, which is not correct. So when in doubt, just use 6 ligands. You really can't go wrong with that most of the time. Of course, it's not perfect, but if you're not looking to memorize a whole bunch of random information, you can use this and it should work for you a lot of the time. So here, this slide should actually be split in two. So complex ion naming is pretty intense. Here we have cobalt, sulfate, and ammonia. So we've got 5 ammonias, penta 5, amine ammonia, sulfato, sulfate, cobalt 3 ion. Complex ion naming is complex. Sad face. You don't need to worry about it. However, you do want to be able to write these net ionics. So the previous, a couple slides ago, it asked us to write the net ionic equation for when a copper 2 nitrate solution is mixed with concentrated ammonia. And here's our answer. So it was copper 2 nitrate, right? Copper 2 nitrate was added to a concentrated ammonia solution. Now, if you're wondering, okay, well, how many ammonias? Well, you could try using that trick of take the charge, multiply it times 2, that's equal to 4. So most likely there will be 4 ligands. So 4 ammonias. And you will end up with this nitrate is going to dissociate off of there, and we'll have copper. It's going to be attached to 4 ligands. It keeps its same charge because ammonia has no charge. It's aqueous. And we know that those nitrates are floating off here. And since we know that copper nitrate is soluble, this is actually going to do that. And we're left with copper 2 plus. And you could rewrite it as what's typed up above. Four ligands. So there's an example of a ligand problem, and you can see that copper has accepted electrons from the ammonia, whereas the ammonia has donated electrons to the copper. La here stands for Lewis acid versus Lewis base. All right, that's it. We are done with notes for this chapter.